Yes, Professor Tom Overbye is our presenter today, and he is one of the PowerWorld Corporation co-founders. It was commercialized. We became a company back in 1996, but Tom had been working on the software that would become PowerWorld Simulator for some years before that as well. He has received his bachelor's, master's, and PhD degrees from the University of Wisconsin. Started his academic career at the University of Illinois at Urbana-Champaign, which is where the PowerWorld Corporation offices are located, not as part of the university, but in Champaign, Illinois. Tom has since moved on to Texas A&M University, where he is the O'Donnell Foundation Chair number 3. And he also is the director of the Texas A&M Smart Grid Center, which if you haven't done so, check out their website and pay them a visit sometime. It's a really neat place where they've got a simulated control room and work on all kinds of neat visualization and simulation research. So with that, I will turn it over to Tom and let him get started.
Okay, thanks, Scott. As Scott said, I'm a professor here at Texas A&M and direct the Smart Grid Center. I was at Illinois, as Scott said, from 91 to 2016. Prior to that, I was at Madison, where I got all my degrees. I also worked as an engineer for Madison Gas and Electric for 8 years. I've taught lots of different classes over the last 30 years. As Scott said, I did begin the development of PowerWorld when I was in graduate school, actually in 1987, and I started it just to learn how a power flow worked, and I've been developing it ever since. Of course, most of the development now goes on with PowerWorld Corporation. I was a co-founder of PowerWorld in 1996, along with Mark Laufenberg. When we started PowerWorld, our goal was to make power system analysis as easy as possible. And when I say that, I do like to emphasize that I don't think it's easy. And I think it's getting more complex all the time. And certainly as we start doing things like HEMP analysis, it's even getting more complex, but we are trying to make it as easy as possible. Before I go on, for those of you who are wondering how can you be a faculty member and still be involved with PowerWorld, both UIUC and Texas A&M do encourage faculty to do consulting and have external business relationships. So I've been doing this for the whole time PowerWorld has been around, so more than about 25 years now. And I should say, as was the case at UIUC, at Texas A&M, my relationship with PowerWorld is covered by a management plan. So they ask that I say that when I give these sort of presentations. Scott mentioned the Smart Grid Center that we have here, and we would love for y'all to come visit. There's an opportunity to come visit at the end of February this month when we have the Texas Power and Energy Conference. The Texas Power and Energy Conference is a conference that we started in 2017. It's actually modeled after a conference that they do at Illinois called the Power and Energy Conference at Illinois. Here at A&M, it's going to be in the Memorial Student Center, and you all are welcome to join us. The website is listed there. I should also say that some of the material from this presentation is in a paper that we recently wrote for TPAC. That paper and others are available on my website, which is listed on slide 4. And these slides, I sent them to Scott, so he'll post them on the PowerWorld website. And as Scott said, there are some example cases that we'll get out to y'all as well. Okay, when we talk about HEMP, it's a challenging event for the grid. So I kind of like to start on a bright note. And I do think our energy future could be quite bright. I hope it will be bright. One of my goals is to help us as we work to develop an electric infrastructure that is sustainable and resilient for the entire world. It's a very exciting time to be in the electric power field. I know I'm talking to some students here, so you've made a great choice if you're in this area. I think there'll be lots of opportunities for you going forward. But as we make this transition, we certainly do have to talk about electric grid resilience issues, including today's focus on HEMPs. So what's the presentation in a nutshell? I'm going to talk about high altitude electromagnetic pulses, or HEMPs, some call them HEMP. The particular focus here is going to be on analyzing HEMPs using PowerWorld Simulator. I did give a presentation about 2 months back for the Smart Grid Center that covered some of this material, but that was more of a general presentation, whereas this one it's got some of that general material in it, but it's also got a lot of material on how to do it in PowerWorld Simulator. The presentation is most appropriate for engineers and students who have some familiarity with electric power system analysis. If you know PowerWorld Simulator, so much the better. If not, there's lots of good material that a lot of it was developed by Scott that can help you understand PowerWorld. If you've been doing geomagnetic disturbance analysis, perhaps at a utility level, that's a plus, but certainly not essential. And I'll try to make the presentation as general as possible. So if you don't fall into the PowerWorld specific category, you should still enjoy it. Okay, so HEMPs are rare events, and an HEMP could be severe. They do have 3 components, E1, E2, and E3, which I'll talk about as we get into it a little bit more. The presentation is mostly focusing on the longer term E3. I do want to start out by emphasizing that HEMPs are severe, but they're not so severe that they cannot be mitigated, at least to some extent, and certainly their impacts on the grid can be simulated. I did enjoy a few years ago reading a book called 1 Second After, which is about the impact of an EMP on the electric grid. The book really doesn't talk much about the EMP. It's more focused on 1 second after and the days and weeks after an event from a small town perspective. So it doesn't get into the technical details on it, but it makes it sound very, very, very severe. I don't think it's necessarily going to be as severe as the book 1 Second After implies. I will say that this presentation is not designed to provide any particular commentary on the HEMP impact of an actual electric grid. It's talking about the modeling and techniques for doing it, but I'm going to use synthetic grids and actually synthetic HEMP waveforms. So there's nothing here that talks about the vulnerability of any actual grid. Of course, the techniques can be used with the appropriate models in the appropriate context to do that sort of analysis, but that's not the purpose of this presentation. Couple reports that are related to this. One is from our National Academy's report. One is the Analytic Foundations of the Next Generation Electric Grid. The other one is Enhancing the Resilience of the Nation's Electric Grid. Both of those are easily available online. When I need to download them from the National Academies, I just Google the title and it pops right up. DOE also had a transmission innovation symposium about 6 months ago, and some of the material that I'm presenting here is in that, not a lot, but it's got some good papers on where we feel the presenters in that symposium feel the electric grid should be going in the next couple decades. So if you're interested, the white papers are available at that site right there. In the National Academy's 2017 Grid Resilience Report, there is a table that talks about different events that could impact the grid in a negative sort of way. The events are listed by first letter there. And then they're put in a graph where there's two axes. The x-axis is the amount of warning time before the event, and then the y-axis is the amount of time to restore service after the event. Very quick occurring events would include earthquakes, physical attacks, potentially cyber attacks, whereas a longer event that would have a lot of warning time would be a drought. In this table, it does not mention HEMPs. And I was on the committee that developed this table, and we did spend some time discussing whether they should be in there, with some people feeling they should and other people feeling they shouldn't. They're not on the graph, but they are certainly mentioned in that report. So what we're going to talk about today is an example of a high impact, low frequency event. This is a term that NERC created, I believe, about a decade ago. Other people call these black sky events. The idea on a HILF event is it could be so severe that we might have to operate in a new normal for a long period of time. Of course, we're seeing that as a society with COVID, where we spent a long time not going into the office and mostly not seeing people. These are the sort of events that could fall in that category. And of course, as engineers, we would like to make sure that the grid is designed and operated in such a way that even if these events were to occur and we did have to go into new normal, it would be as short as possible a new normal. We hosted here at Texas A&M the North American Power Symposium last November. It was one of the first in-person conferences that was taking place, and it was a delight to see everybody. And as I said, we hope we can see a lot of you at TPEC coming up at the end of the month. But at the NAPS event, one of the keynote speakers was Dan Smith from the Lower Colorado River Authority here in Texas, and he presented a slide that talked about the reliability resilience continuum. And when I saw this, I've been working on the EMP events, and I saw that EMP was the one furthest on the right in terms of resilience. I asked Dan if I could use his slide, and he said, sure. So we're talking about an event that at least the North American Transmission Forum thinks of as the most that would stress the grid in terms of resilience. Whereas on the other side, the reliability, those are more common events, a thunderstorm, a flu season, a single transformer vandalized. So we're kind of on the far side of stressing the grid with this one. So what is grid resilience? Again, I borrowed a couple of slides from Dan. There's different definitions of grid resilience. I won't go through all of them here. There's one from the dictionary, one from FERC, one from NARUC, and then EPRI and the North American Transmission Forum have one. The gist is it's a severe event, and the goal is to recover with as little disruption as possible in a reasonable amount of time. There's certainly going to be disruption, but you want to be able to bounce back quickly from that. So that's the goal with these more severe types of events, and people are definitely putting an HEMP in that category. Okay, the grid needs to be resilient to lots of different disturbances on lots of different time frames. I like the slide on the top, which I got from one of my friends, Tracy Ralstad. It's actually a trampoline that flew into some 115 kV transmission gear and caused an outage, but it was a pretty minor event. On the bottom right is a picture of what could occur during an ice storm. We certainly hope that that's not what is going to be occurring today, and I don't think the amount of icing we're supposed to get is anything near what Quebec got in, I believe, the 1980s that knocked down their transmission tower. But there's certainly different sorts of events that can stress the grid. One of the key graphics that explains how we operate the grid was presented by Les Fink and one of his colleagues back in 1978. And the gist is normally we're in a N-1 reliable condition where it's just tradition, or it's just standard operations. The grid is working as it should. Then you can go into alert, emergency, and they also set up an operating state called in extremis. And in extremis is where heroic action is needed to save the grid from a collapse of either an entire interconnect or a large chunk of an interconnect. That's the sort of operating state that we're talking about here. I don't think they have an arrow that goes from in extremis back to the other ones without restoring it first. But the idea is hopefully with in extremis, you don't have to restore too much of the grid. And that's what we'll be trying to do with the HEMP, is to not lose a lot of the grid from the events. Okay, different time frames on the electric grid. This is from the book by my Illinois colleague, Pete Sauer and M.A. Pai. The time scale from seconds goes from less than a microsecond out to weeks and months and years. HEMP falls in the time frames that can go very fast. And when we talk about an E1, we're talking about less than a microsecond. And then E2, which sort of looks like lightning, so it kind of fits in the lightning propagation. Usually when we study HEMPs, we don't do much with the E2 because we think of it as lightning, and the grid is pretty well protected from lightning. And then the focus here today is on the longer term E3. What we want to do with these severe events is go through this graphic here, that what do we do before the event, what do we do during the event, and what do we do after the event, and then how do we learn from the event. The focus here on the HEMPs is going to be mostly on what can we do prior to the event to plan for it and hopefully be prepared, and then what could we do during the event. But certainly planning for after the event and planning on how you learn would be important as well. But the focus this afternoon is mostly on 1 and 2. Okay, so how do we approach these HILF events? The goal here is not usually to replicate a specific event. And sometimes people want to replicate specific events, and certainly that can be a good thing. But the challenge we often run into is many of these events have not occurred. I mean, we haven't had a HEMP on the electric grid. We haven't had a severe cyber attack in this country. We haven't had a severe physical attack. So it's harder you can't replicate an event that hasn't occurred. And also, it is not to ensure that there's no loss of service, because in some of these events, we are going to lose service. It's just how do we minimize that and how do we bounce back as quickly as possible. And in doing this, I do want to emphasize that we have to do a reasonable cost-benefit analysis. Certainly, that's a challenge when you have so much uncertainty on the cost side and so much uncertainty on the benefit side. But I'm going to show you today that we do have techniques to simulate these events. Of course, as a researcher, I always like to say more research is needed, and it certainly is here. But I think we've made, as an industry, pretty good progress in studying these events. Okay, EMPs. A lot of the people here, of course, know a lot about EMPs, but not everybody does. Broadly speaking, electromagnetic pulse is just any transient burst of electromagnetic energy. Could be from a spark in an engine, lightning, electrical switching. Could be a geomagnetic disturbance, or it could be caused by a nuclear weapon or a non-nuclear weapon. The focus here is going to be on what we call high altitude electromagnetic pulses, which are caused by nuclear detonations at higher altitudes. Naturally, not all the information on nuclear EMPs is public, but there are public documents. So in preparing this presentation, I tried to leverage. What I used for this presentation were public documents. So the primary concern about nuclear EMPs is their impact on things like the grid. The common nuclear impacts from a burst that occurs closer to the surface would not occur. So this would be something where you wouldn't have a blast thermal radiation affecting people on the ground. The explosion would take place at an altitude ranging from dozens of kilometers up to hundreds of kilometers. And then it could have a potentially large impact. And, while there might just be a single event, we would have to consider the fact that simultaneous events could occur as well. Okay. Now this is the one where I have to click it twice. As I said, there's three major parts to a HEMP. There's the E1, the E2, and the E3. The graphic there shows on the x-axis the time scale ranging for the E1 really in the nanosecond stage. And then on the y-axis, it's the magnitude of the electric field on a log scale. So with the E1, you have very high fields, but they're very short. And the issue with E1s is they can impact unprotected electronics. E2 kind of looks like lightning, so it doesn't tend to be talked about too much. And then E3 is the focus here. It's got a time scale on the order of seconds out to a couple of minutes. The scale of the E3 in terms of electric field strength is on the order of a geomagnetic disturbance, but it can be higher than a geomagnetic disturbance. This is a little bit of history. I talked about this in my earlier talks. I won't go through it too much in depth, but EMPs go back to the start of the nuclear age. A lot of information was gained on EMPs from an event that was called Starfish Prime that took place in the early 1960s, and some of the references didn't note about what happened during Starfish Prime. Nuclear tests in the atmosphere, space, and underwater were banned in 1963. So after that, the actual physical data on EMPs wasn't coming in. So a lot of this is based on those earlier tests and then what people theorized would occur. Okay, in doing the studies here, the goal is to have access to waveforms. There are various sources of waveforms that are available to anyone. DOE has put out a waveform. The EMP Commission has put out a waveform. DITRA has put out some waveforms, and some other entities have put out waveforms. So what I did for preparing this presentation was leverage what was available in those documents. And I'll get into the particulars in just a second. What are the overview of the threats to the grid? E1, we would be talking about potential loss of load, potential loss of generation, and potential damage to the protection system of the grid. And that's certainly a worthy area of study. It's just not the focus here. E2 might cause voltage impulses on the transmission system, similar to lightning, and we could get some insulation flashover, but it doesn't tend to be a key focus. On E3, the focus is on causing what's known as geomagnetically induced currents in the grid, or what we call GICs. These GICs are quasi-DC currents. They're slowly varying with a frequency of much less than 1 hertz. What happens is they superimpose on the AC signal, 60 hertz in this country, and that can cause saturation in the transformers. And when the transformers saturate, they get harmonics. And when they get harmonics, that causes increased reactive power loading in the positive sequence on the transformers, and it can also cause heating damage to the transformer. The focus here is mostly on preventing cascading grid collapse caused by this increased reactive power loading in the transformers. But at HEMP, some people say could cause heating damage on transformers. This is one of the E1 waveforms. I've given the source there. The E1 has, again, a pulse that's very fast. The scale is nanoseconds, a high electric field, 50 kilovolts per meter, and it could impact electronics. The graphic on the right, it's a little hard to see, but those ovals are superimposed on, or I guess circles are superimposed on the country. You know, it goes pretty much from coast to coast there. So the E1 would have a footprint that covers a good chunk of the country, but the magnitude of the pulse certainly falls off. It's highest in the bullseye and then falls off as you get further out. So the actual bullseye area is not that big. Okay. Again, the focus here is E3, but we do have to consider E1. E1 would impact the grid in the sense of causing relay issues, maybe communication issues, maybe SCADA issues. But those issues can be reduced if you correctly shield your devices. There also might be indirect impacts, certainly if a lot of people lose load because of an E1, that lost load is going to impact the grid. And I'll show you a way that we can simulate that as well. Okay. E3 impacts are caused by the burst perturbing the Earth's magnetic field. In that sense, they are related to what would occur with a geomagnetic disturbance. A geomagnetic disturbance is caused by a solar event, a coronal mass ejection on the sun. Charged particles come to the Earth at several million miles per hour, and those charged particles impact the Earth's magnetic field. When that occurs, you get a change in the magnetic field, a dB/dt. Usually we express that in terms of nanoteslas per minute. This induces a non-uniform time-varying electric field at the Earth's surface. And to correctly model that electric field, you need to understand the conductivity of the Earth's crust going down potentially hundreds of kilometers. So what you see at the surface, the electric field that impacts the transmission lines, is dependent upon what's going on in the crust of the Earth. That's just a graphic on the Earth's magnetic field. The only reason I showed is just that people understand how big our field is in terms of nanoteslas. It kind of ranges from about 20,000 in the South Atlantic up to 60,000 as you get closer to the poles. So if you've got a magnetic field that's 60,000 nanoteslas, you can only change it at a rate of, say, 5,000 nanoteslas per minute for so long before you just run out of field to change. So the HEMP is going to be impacting this field, and as that field is impacted, it's changing with time. By Faraday's law, change in magnetic field induces an electric field, and when you've got an electric field superimposed on conductors, like our high voltage electric grid, you get currents induced, and those are the GICs. Okay, so this is a graphic that came out of an Oak Ridge report from 1985 that shows how the Earth's magnetic field was impacted by the starfish prime event. Checkmate and Kingfish were part of that operation. I guess they were part of operation. Well, Starfish was part of it. The change here is pretty high. If you look at how the field is changing from 200 down to minus 700 in just a couple seconds there, that's a pretty fast in terms of nanoteslas per minute. In a GMD, a strong GMD would cause a change of about 500 nanoteslas per minute. That's what occurred in Quebec in 1989 that caused a blackout of the province of Quebec. A larger GMD, such as occurred in 1859, known as the Carrington event, might cause a variation of 2,500 nanoteslas per minute. So certainly HEMP could cause a higher variation than even the worst GMD. The key difference, though, is the duration, and we'll get to that in just a sec. There are various recommended E3 waveforms. So when we do these studies, we would like to have some waveforms to study, and that'll be a key input to what I'm going to present in just a second. The DOE put out a recommended waveform. I think I listed the reference in an earlier slide there. With the E3, it's actually divided into two components. There's a blast waveform, it's called the E3A, and then there's a heave waveform called the E3B. Both of these waveforms have a variation with time, and that's what's shown in the graph here, which I got from the DOE document. And there is also a spatial variation. And in this particular document, it doesn't show the spatial variation. So we just have the change in time. A little bit of background, which I will not dwell on, but it kind of in the blue box there, when they present a waveform, that waveform is an electric field, and it uses an assumed ground conductivity, 10 to the minus third Siemens per meter here, which is certainly a reasonable value for the US, but it's not a value that applies everywhere in the US. So if you want to apply this waveform in places where that assumption is not valid, you have to go through some analysis. If you can assume the Earth is has a single conductance, then the analysis is pretty straightforward. The challenge, though, is that the Earth does not have a single conductance, so it gets trickier to deal with. From the point of view of this presentation, we are just assuming that somebody provides us with an electric field. As long as the electric field is provided, then we can do the analysis. This would be the details that go into calculating the electric field, but it's not going to be the focus of this presentation. Okay, that graphic just shows some of the different soil conductance values. It's not really related here. I just wanted to put it in context, but the value that DOE assumed is a reasonable value. It's kind of right in the middle of this scale here. Okay, there are other documents that are available that tell us the time-varying spatial footprint, or at least give examples of a time-varying spatial footprint. One is the document that DITRA put out. ARA, I think, did the work on this. And I mentioned the specific document earlier. This shows a snapshot of the spatial variation in the electric field, where it goes from blue is 0% a maximum and red is 100% a maximum. The image on the left has a maximum of 1.5 volts per kilometer, and the image on the right has a maximum of 15 volts per kilometer. Both of the circles have an extent of, I believe their diameter is about 1,100 kilometers, roughly the distance from St. Louis to Washington, D.C. So they cover they would cover a good chunk of the country, but not at a uniform magnitude. The values also change with time, and again, referencing that DITRA report, they show here a couple snapshots of how the fields would change with time. The going across is at 20 seconds, 40, or I guess it's 40 seconds, 60 seconds, and 90 seconds for the top row. And that's for a burst latitude of 14.5 degrees. The other two are for burst latitudes closer to what we would see in this country. The takeaway from this is that the field is not uniform and its shape is time varying. So that's something that we have to take into account in our analysis. Also, we're talking about vectors here. So they have a magnitude and they have an angle. This graphic is it's a little hard to see, but what the images are showing there are just the direction of the electric field caused by these different events. If you want to get the original, again, it's from that same document that I just showed. This is just figure 8 here. But when we do this, we have to have a magnitude and we have to have a direction. So you'll see that in the examples coming up. Okay, so when we have a time varying electric field and it's superimposed on the transmission grid, because the time varying electric field is changing relatively slowly, we call it quasi DC. It's varying with time, but it's varying at much less than a hertz. So from an AC perspective, it looks like it's DC. So the electric grid just looks like a big DC circuit. The electric grid itself is 3-phase, but all of the conductors from a DC perspective look like they are just parallel. So how we model these electric field variations along a transmission line is we just integrate the electric field along the length of the line. It looks like a DC current, it looks like a DC voltage. We just take that Thevenin equivalent and create it into Norton equivalent, and that allows us to solve the electric grid as though it were a DC circuit. As we're solving this DC circuit, we do have to augment it with some additional fields that are not in a typical AC analysis. These include how your electric grid is grounded through the transformers. The delta windings don't have a ground path, but the Y windings do. And then we also have to know the substation grounding resistance. Luckily, from an HEMP analysis, these are values that utilities now have because of the work that they've done in GMD analysis. So while these are newer fields to deal with, they're ones that electric utilities do have now. Okay, once we've set up our DC circuit, it's very straightforward to solve. It's just basic circuit theory to solve these. They're larger matrices that you have to solve, tens of thousands or maybe hundreds of thousands of equations, but nothing that is beyond what is actually commonly done in power system analysis. So the takeaway is that we can, from a known electric field input, we can easily calculate the GICs on an electric grid. Again, there's some issues that you have to go through. What about delta windings, transmission and distribution transformers, things like that. But because NERC requires the utilities to do GMD studies, they all have this information and they're using it. So it is now available. So we don't have to dwell on that. This is a simple example of calculating the GICs. It's really just solving DC circuits, and if you're used to doing power flows on AC systems, it's actually much easier than that because it's DC. So this is something that PowerWorld has built in. Okay. The calculations to get the GICs are actually very fast. They're faster than the AC calculations. So when we study HEMP in PowerWorld, we are actually evaluating the GICs when we do a simulation every time step, so it goes very fast. And the GIC calculations are not a constraint. Okay, how do they impact the transformers? Increased reactive power lossing, that causes harmonics, and those harmonics cause the potential heatings and the potential voltage collapse. Okay. And then the last one before I get into the PowerWorld simulations is when you've got GICs, the question is how do they impact the transformers? They impact the transformers the same way the GICs would impact the transformers if they came from a GMD. A lot of people use a linear model that says if you have so many GICs in a transformer, it maps into so much reactive power loss. We can also use nonlinear models, and PowerWorld supports linear and nonlinear models. Knowing the K value for each transformer is important, but again, this is the same value that utilities would have for their GMD studies. So there's nothing that is beyond what's already available with this. Okay, HEMPs are similar to GMDs, but there are some key differences. One difference is they're much faster. E3 is much faster. It has a rise time on the order of seconds, and then it might last for minutes, whereas a GMD would last potentially for hours or days. The takeaway on this is that the E3 is typically simulated using stability simulations, what is commonly called transient stability in PowerWorld lingo. So we've got the EMP analysis built into the transient stability in PowerWorld. A second difference is because the E3 is preceded by the E1 and E2, their impacts need to be considered. That will be treated as an initial condition in the time domain simulation because the E1 and E2 are so fast that they would be over before we really start the simulation. HEMP would occur with little or potentially no warning. This is in contrast with a GMD where a geomagnetic disturbance or the solar event would be observed at least a day ahead of time. We might not know where it's going to strike, but we would know that something's coming. That would probably not be the case with the HEMP. The faster time scale on an HEMP is there's really no time from operator intervention. Operators can respond quickly, but they're not going to respond within seconds. But there is the potential for automatic EMS level mitigation to occur. So we're going to talk a little bit about that going forward. We don't have any operational experience with HEMPs. We do have operational experience with GMDs. Like I said, a large GMD occurred in Quebec in 1989. Smaller GMDs occur regularly, so we do have some operational experience with them. The other thing with the HEMP, as opposed to a naturally occurring event, is an HEMP implies an adversary, and the adversary would have some control on the time and location of the event. So it might not occur at a convenient time. Okay. In modeling these in PowerWorld, we pretty much take what we would have for a GMD study as power flow data plus location information and some of the GMD specific parameters I mentioned. We would then take a standard stability model, and this is something that utilities have and use all the time. We might want to augment that with some of the protection system beyond what's already in the stability model, but if it's not there, there are ways to make reasonable estimates. And then what we need is a time and spatially varying electric field. This can be provided in several different ways, but the easiest way for PowerWorld to get this is through what's known as a B3D file. The B3D just stands for binary 3D file. It's just a file format. It's a way of expressing spatially and time varying information. That information could be anything, but in the case of an HEMP, the information is the electric field magnitude and angle at different locations in the study footprint. For these slides, as I said, I'm not going to talk about any actual grid. Luckily, a lot of work has been done, some of it by folks here at Texas A&M, on developing synthetic electric grids. These are fictional grids. My Wisconsin colleagues like to call them realistic but not real. I think that's a great phrase. We're going to be looking at a realistic but not real grid that covers the state of Texas. I do want to emphasize that it's realistic in the sense that it's a grid that could be built, but it in no way implies anything about the actual Texas grid. It could be stronger, it could be weaker than the actual grid. It's just a grid. It's a fictional grid. We like to call it good fiction, and we think it is a good grid, but it has nothing to do with the actual grid for ERCOT. Okay, so the case setup is identical to what's done for a GMD. We map buses into substations, and they have geocoordinates, and they have grounding resistance. We have grounding configuration information on all the transformers. We have models relating the transformer GICs to the reactive power losses. We have stability information. This is all information that would be contained in a PowerWorld PWB file. The PWB, which just stands for PowerWorld binary file, is the way PowerWorld specifies electric grids. For this presentation, I created a file called TSG, that just stands for Texas Synthetic Grid Company, HMP start. This is the dynamic models that are in that case, and as Scott mentioned, we'll upload this case to the website afterwards so you can have access to it. Compared to an actual stability model, it doesn't have as many different types of models, but it's got a reasonable number of models in it, so it's a good place to start. This just shows if I did a time domain simulation on this grid for a more standard disturbance, nothing to do with HEMP. If I just lost 2 generators, what would happen is when the generators are outage, the frequency would go down, the grid would oscillate around, and it would settle out at a new frequency, and eventually it would recover. But that disturbance would take place on the order of tens of seconds. So it's the same time scale as an HEMP, so that's why we use this tool to model HEMPs. Okay, one issue that came up with studying GMDs and HEMPs is when you solve a power flow, you usually just open generators and you don't take out the generator step-up transformer. This is something that when we've been looking at cases for real grids and our synthetic grids, it's very common that generators are open and their step-up transformers are in service. That has no impact on the power flow, so that's why people can do this. What we found, though, is that whether you have a generator step-up transformer in service or not is a path to ground, and that affects your GMD study and this affects your HEMP study. So what PowerWorld has recently done is actually provide a way that people can tell whether the GSUs are in the correct status. So I won't dwell on this, but the starting point for an HEMP study is to make sure your generator GSUs statuses are correct, and we've provided a way now to do that. And that's what that slide shows. Then in PowerWorld, the starting place for a HEMP study is to load a B3D file. I should say that doing these studies requires that you have the PowerWorld GMD add-on, maybe it's called the GIC add-on, and it also requires that you have the PowerWorld stability add-on. So that would, both of those would be required to do those studies. I'll go ahead and this is a PowerWorld that has that case loaded, the 2000 bus case, and then PowerWorld has an add-on GIC right here, geomagnetically induced currents. If you go to that form, it has a number of different tabs on it. One is to do single snapshot GIC analysis, which is for GMD studies. There's also a tab that's called the time varying electric field inputs. That's where you load up the B3D file. So if you just select that tab here under calculation mode, it brings up this page, and this page is where you load a B3D file. We've got various options for setting up or getting a B3D file. You can either auto load the B3D file. It's a separate file. If I were to browse here, I would see in the example a file there. I could load that file, which I've already done here, or I could actually save the B3D data in the PWB file. There can be a lot of B3D data, so that's a potential concern, but it is something that you can do. What a B3D file has in it is it's got a bunch of time points, and in this case on the bottom left, I've got 60 time points, and it's set every 1/10 of a second. And then at each one of those time points, I've got a grid. It doesn't have to be a grid. It's just a set of points that at each point, it expresses the electric field at that point and at that time as a magnitude in the east direction and a magnitude in the north direction. Alternatively, we could call it a magnitude and an angle. The two are, of course, identical. This page gives you a number of options for dealing with that B3D file, which we'll cover in a little bit. So going back to the slides, I've shown you that here. I will say that for this presentation, I made up a fake B3D file. So this B3D file is, I called it a test B3D file with an example fictional HEMP E3 waveform. I could not find a waveform, a public waveform that had both time and spatial variation. I think as the industry, we need to have those available. I just couldn't find one. So because this is a public presentation, I just wanted to make up something that's totally fake. So I just kind of looked at some of the documents like the DITRA document and the DOE waveform, and then just made up something that essentially, when you see it, it's kind of simplistic. It's sort of like a donut with some time variation that is just a 1 minus a cosine function. Okay, so that's the waveform. The page gives some options for working with the B3D file. You can save it in the PWD file. You can select a set of points to save in a B3D file. You can do some scaling on the B3D file, and then you set up the time varying series. The setting up the time varying series is the important part because that's going to provide the input into the stability simulation. The grids on the bottom, which I just went through, the one on the left is the time points and the one on the right are the time point grid preview. These show you the electric field inputs in a tabular form. We did add the ability to make it easy to show this information graphically. I've gone through a procedure here to show you how you can contour it. If you follow that procedure, what you would get for the waveform that I put in, and this is, it kind of looks like a donut because it's just a fake waveform that I made up just for this presentation. It's got spatial variation. I move it around a little bit over the course of the simulation. The simulation I'm running in these slides just goes from 0 to 60 seconds. The electric field maximum goes up to initially about 30 volts per kilometer. This is, if it looks like 1 minus a cosine waveform, that's what it is. I guess that's a cos, yeah. So one minus a cosine. I mean, it's just some simple function that I made up. It's essentially just a cosine waveform. So that's what we're going to simulate here. Again, the idea is when you do an actual study, you're going to have a more detailed waveform. Okay. Then in PowerWorld, if you click up here, set up time varying series, what it does is it takes this data and it maps it to each one of the transmission lines. So when I click that, it maps it into the transmission lines. If I want to see that mapping, if I just go up here, time varying series input, this is the time varying series input that is going to go into the stability run. It's just a bunch of points that vary over time. Here's the first time point, 0 seconds, 0.1 seconds, 0.2 seconds. So that's what we're going to be simulating. And then this is just a voltage on each one of the transmission lines in the case. Let me move that over there. And because this is a 2,000 bus case, I've got something like 3,000 transmission lines. And I just am taking that data and running it into the stability program. Then the stability program is going to evaluate it because it's got the actual voltage on the line. If that line goes out of service, then that voltage source is taken out in the GIC calculations for that time point. So this is what goes into the stability simulation. And then running the HEMP simulation is pretty straightforward. You just have to click on the GIC analysis form, include GIC and power flow and transient stability. So if I go back to PowerWorld, that field is right up here, include GIC and power flow and transient stability. If you click that, then this waveform is going to be included when you do a stability run. So the next step is then just to go to the transient stability analysis form and set it up as you would a regular transient stability simulation and click run transient stability. So if I were doing it for this set of inputs, this is the GIC form, I would go add on transient stability, and it just does a stability run. And that form's opening right now. So this is the stability form. Usually in a stability form, you have a set of events down here. I don't have any events defined because I'm going to be using that electric field as an input. So if I click this run, and of course, this requires that you understand how to do the stability simulations, how to save options and stuff like that. You would just click run stability and it starts doing a stability run. And if I bring the graph over here, it's running the stability run. The voltage is changing a little bit. The reason why the voltage is changing is because it is simulating the HEMP. So I'm going to actually pause it because I don't want to go through the whole 60-second simulation. I'm going to, I guess I already, I'm going to reopen this case because it's got results on it. So this case, I ran it earlier today, and it has the stability results. So when I go to add-ons, transient stability, it has saved in it all the stability results for this particular HEMP study with my donut that went up to 30 volts per kilometer. So if I look at plots here, and I wanted to plot, say, all the voltages, I generate the selected plot coming up on the other monitor. But this shows right here, and this is in, I think, the next slide. This shows the voltage variation at all 2,000 buses in the case over the course of the simulation. This is per unit voltage. This sort of graph would be very familiar to people doing stability runs. It would go, as the HEMP is occurring, it's depressing the voltage. So that is what we covered right there. The challenge then is, after you've done the study, is to make sense of the results. So this is what I just showed you, the 2,000 bus voltage variation. PowerWorld has lots of different ways to visualize results from stability runs, and a lot of them we leverage here. One example is I can set it up so I can visualize at any point in time. This is 30 seconds into my study. I have a one line, and on that one line, I visualize the electric field, and then I put little arrows on there that show the variation in the direction of the electric field. Again, this is a fake waveform, and all I did was I put like a kind of a little donut here, and then I had the electric field rotating in a clockwise direction around the center of that donut. And then if you actually simulate it, you'll see that I just moved the donut around a little bit. It's not, again, meant to be an actual HEMP waveform. It's just meant to be something that we can use in training and put on our website. Okay, so in doing this, then as we do the analysis, we've got all the electric grid results. For example, here is a graphic that I created showing the voltage magnitude depression caused by the HEMP at 30 seconds. I show how much reactive power losses there are there. And then you can use this, and here I'm showing how the real power is flowing in the grid, and the yellow arrows are showing how the GICs are flowing in the grid. I can look at that at any point in time throughout the simulation. And let me just show you this. PowerWorld has a newer feature that a lot of people don't know about, but it's actually something that is extremely handy, is when you do a stability simulation, there is an option that if you click it, it stores a full power flow state every once in a while, and how often depends upon what you set here for the parameter. I've got it set to store the full power flow state every quarter of a second, 30 time steps here. And then you get in the results here, when you do that, you have access to power flow states at all the different points in time. So if I wanted to look at the power flow during this study at, say, 30 seconds, I would just go to power flow states, and I would see a listing of the stored states. And I could, if I right click, transfer that to the power flow. And then the power flow looks like we're at that point in time. And at that point in time in this study, the voltages are kind of depressed. So we would see the depressed voltage, and you can study that state if you want. Okay. So I use that all the time, and it's extremely helpful for understanding what's going on during a stability run. Now, if we decided we don't want to study 30 volts per kilometer, but we want to study something higher, PowerWorld has an option on the GIC analysis form to just scale our B3D. It's shift scale or stretch the grid. This just scales it. In this example, I scaled it from 30 up to, I think, 75. 75 didn't work too well, so I backed off on it. In putting in this option, we do want to be clear that we're not implying that this is correct from a physics of a HEMP. The best way to model an HEMP is somebody provides you with the electric field data in the form of a B3D, then you go from there. That would be the best way to do it. But if you're a utility engineer and you have a waveform, and you know, let's say it's 20 volts per kilometer and your grid's fine, you might want to say, well, what if I double it? If you want to double it, just put 2 in here and you can scale it. If you want to shift it in latitude and longitude, you can shift it in terms of latitude and longitude. Again, because the waveform is going to depend upon the latitude and longitude of the blast. Not saying that that's completely correct from a physics point of view, but we do recognize that people are going to want to do this when they're doing this analysis, so we made it as easy as possible. What I typically like to do is I will scale an event and go up to a critical point. The critical point is where I lose a solution. In this case, I went up to 52 volts per kilometer. These are my voltages. If you know voltages from a power system point of view, you know that as you're getting values down to below 0.8 and 0.7, you're stressing the grid. And this was clearly a stress grid. If I tried to go above 52 volts per kilometer, the system did not solve. This is the frequency variation. Again, I can look at full details here. I took that more stress situation and said, hey, what's going on in terms of the grid at that point in time? I contoured my voltages at 30 seconds, very easy to do because I had saved the power flow states. I do want to note that I did change the contour scaling. So 0.7 is dark red. This is a very stressed electric grid at this point in time, but you can see that the stress is in this area. The rest of the grid is in fairly good shape. So from an operational point of view, if such an event were actually to occur, one mitigation strategy would just be to say, we're going to cut off that part of the grid. You know, that's what a utility engineer would have to do if they're developing a mitigation strategy, is figure out what in extremis save the grid sort of controls they'd like to do. And this is a tool that lets you figure that out. Okay, what about the E1 impact? The E3 would be preceded by an E1. The E1 could do lots of different things to the grid. It could impact your protection system. It could take out components. That would all be considered in E3 study as a change in the initial condition. So that's what we would do, is we would load that as an aux file. Now, we did recognize that it's pretty common that a utility engineer would say, hey, if a E1 were to occur and it took out some of my load, I want to study that from a stability sense. And I know that if I lose load, I'm going to have an overfrequency. So what we did is we put in, currently it's a very simple method for modeling the load that might be lost as a result of an E1. It kind of looks like a big red blotch here on Texas. I'm just contouring how much of the load is retained. For most of the state, I retain all of the load. And then where I simulate the E1 footprint, I just have it so up to a maximum of 25% of the load is lost. And these are all values that you can easily set. There's on the field voltage input, there's an E1 page, include E1 effects as initial conditions. Then you say, where do I want to put my initial waveform? It's a circle. How big is the circle? What's lost in the middle of the circle? And we've got options for maximum percent, the diameter. We can have part of the circle where you lose everything. And well, I guess that's not lose everything. That's the size of the bullseye here. We fully expect that as people look at this, they will say, hey, we'd like something different, and we can easily code up something different. I do want to emphasize, because some people say, well, I don't want to do that. And if you don't want to do it, just don't check it. It's not checked by default, so you don't have to do it. If you do it, it turns out that a lot of times the lost load, I hate to use the word beneficial because this would model load that might be potentially destroyed as a result of an HEMP. But from keeping the grid together point of view, losing this load has some beneficial aspects to it. If you look at the frequency, when that E1 occurs, we get an initial rise in frequency because we lost a bunch of our load. The grid oscillates around and settles down. Then the E3 occurs, and that causes the larger voltage depression, but it's less of a voltage depression than would otherwise occur. Impact of assumed load models. If you do stability studies, you know that the load model has a big impact. In doing the examples here, I use the more detailed composite load model. got 130 parameters per load, is one that is commonly used by the electric utility industry. You know, it's sort of like it's the best load model to use, but it's also computationally more burdensome to simulate. I did do some studies looking at simpler load models, and you might want to use a much simpler load model, particularly if you're just doing screening studies to say, hey, how much can we take as a grid? So you might do a simpler load model in PowerWorld, and you know, in any stability program, the simpler model is going to run faster. Okay, dealing with more stress scenarios. If we go above 52 volts per kilometer, this grid will not solve. It will have a voltage collapse. Would that actually occur in practice? No, that wouldn't occur in practice. The protection system would be coming into play. If you've got depressed voltages and high currents, of course, that's going to look to your distance relay like a fault. So we think going forward, we need to be augmenting the grids with some of the protection system, particularly the distance relays. They're not typically included in stability studies, but that's something that as an industry we might want to include. We do have ways in PowerWorld to set up kind of generic distance relay protection, and that's kind of the next step that we're going to be doing as we go forward with these studies. Automating the process, what I've shown you is kind of the nitty-gritty details of doing a single study. That can be very beneficial for an engineer to go through, and we would, you know, if people have access to these waveforms, or somehow you can get a waveform, it might be that NERC is eventually providing waveforms, then you would want to go through some studies kind of using this manual process. Eventually you'd want to automate it, and we do have ways to make much of this very automated, so that's where we're going next. An important value in doing these automated studies is just to know what's the maximum tolerable electric field. Sometimes the waveforms you get are quite small. For example, in looking at that earlier document that I mentioned from DITRA, some of the waveforms in there are less than 2 volts per kilometer. That's a value much below what is commonly studied in GMD analysis. We know that from doing GMD analysis, 2 volts per kilometer is not going to affect most grids. So sometimes you're going to, a lot of times I think we're going to just run a waveform and say, there's no impact. It just all fine. And that's certainly something that can be automated. Then the trick is to say, well, if this were to occur, if there were an HEMP, what would I do to mitigate it? Like any aspect of grid operation, when you develop a mitigation strategy, you're talking about some sort of protection system. Because of the speed here, it would have to be automated at least to some degree. You have to strike a balance between cost and benefit. HEMPs do certainly present some unique challenges here. What is the cost of a HEMP, and what would be the benefit of having HEMP protection? Both of those have a lot of uncertainty associated with them. So that's a given. But in developing the plan, I thought some reasonable assumptions would be, look, the HEMP would occur with little or no warning, so you have to prepare ahead of time. The HEMP size and location would not be known ahead of time. You'd probably have reasonable upper bounds on the size, but the location you're not going to know. So you have to look at a variety of different locations for the event. An automatic system, a key part of the mitigation is to know, has an HEMP occurred. The good thing about a HEMP from a detection point of view is they do have a pretty unique signature. You're going to get a lot of harmonics in your transformers very quickly. So I think that within seconds, you could set up an automated system. You could set up an automated system to within seconds determine that a HEMP has occurred. So an assumed input to further mitigation plans are, we know an HEMP has occurred, so we're going to have to potentially take drastic action. Given the time frame, you're not going to be able to assume the operator can do anything. They can't respond within seconds, and as we get out into minutes, maybe they can start to respond, but it would be mostly over by then. They'd probably have measurements available. The time frame is such that SCADA measurements would be available. PMU measurements would be likely available. You're not going to have a state estimator probably. Snapshot during the time period, it's just changing too fast, but you're going to have measurements, so you could use that in your control. So you might set up a mitigation strategy that says if an HEMP has occurred and the voltage is below this, shed this load. I think that given the time frame of seconds, we could implement a lot of the mitigation at the EMS level as opposed to implementing it at a substation level in protection devices. There would be potentially seconds, dozens of seconds, at least a dozen seconds to respond. So that means that EMS could send out some controls, and we've got tools to develop these plans now. Okay, so in doing a mitigation, you have to differentiate between a small event that doesn't need any heroic action and a severe event. And sometimes a severe event might occur in part of the grid, but not your part of the grid. So it might be a severe event, but it's not affecting your portion of the grid. But even in that situation, you might have a cascading event coming, so you do have to be prepared for that. It goes without saying, any mitigation plan is going to be system specific. I was going through developing kind of mitigation on this 2000 bus system, and some of it I put in that paper that I mentioned for TPEC. It involves some studies and testing out different things. Some general thoughts I have is probably adaptive islanding is going to be a viable thing to do. So you might want to think about, could we set up islanding at the EMS level to work during an HEMP? The challenge with the 2000 bus synthetic grid is that it's not set up well for islanding. It's not as chunky as some actual grids, but we are working on that. Rapid load shedding is usually a helpful thing to do. And again, if this is a severe event, heroic action is called for. So, we experienced load shedding in Texas a year ago, and of course, a lot of people didn't like it, but it was really a heroic event that was needed to save the system. That would be the same case here. So we might have to do that. You might set up pre-programmed transmission and generator switching. If you've lost load as a result of the GMD, it's going to have an overfrequency. So selectively removing some transmission and their associated transformers could be helpful. Your transmission lines would be potentially less loaded because some load has already been lost. Opening up some transmission lines, which are, of course, picking up the electric field to begin with, so that gets rid of GIC sources. We might want to try to spread out the GICs if it's a more concentrated footprint. Then spreading out the GICs might be more useful, and that could be done by opening certain generators that removes path to ground. It could be opening transformers between, say, in the 2000 bus case, we would open 500 to 161 kV transformers, or sometimes 161 to 115, and that seemed to help. What I like to do is I'll run a scenario when it's most stressed, kind of the highest load that I can get, electric field loading that I can get, and still have it solved, and then pause the simulation. Or I don't even have to pause the simulation. I just run the full simulation, and then I use the power flow snapshots to initialize the power flow at those stress conditions, and then test different scenarios. The idea is you want to develop some implementable rules of thumb. that might be, for example, if A, B, and C have occurred, then do D. And it might be A is that HEMP has occurred, B might be the voltage at this bus is below 0.75 per unit. You might not have a C, and you might just shud that unit. Or you might have A and HEMP has occurred, B might be the frequency is above 60 hertz. C is that generator isn't too heavily loaded and has a lot of GICs on its transformer. Then we might open up that transformer and associated generator. This is some options on transferring to power flow. If you go out to my website, there's actually a paper that explains this in more depth, but it is something that I use all the time in doing these studies. This is a mitigation example where I went into this 52 volt per kilometer scenario, and I paused the simulation at 28. I didn't pause it. I ran it, and then I used the save power flow snapshot to go back to 28 seconds, and then started playing around with the system. For example, I looked at the bus voltages and said, hey, I've got a voltage at a load bus that's 0.5 per unit. The customers at that bus are not too happy. Maybe we should get rid of that bus, or at least its load. I got rid of the load, and that caused the voltages to recover. PowerWorld has lots of ways to do interactive visualization. This is one where I was using some of the newer visualization techniques to look at what was going on in the vicinity of that bus, and I got it set up to visualize GICs and real power flow. This is looking at the heavily loaded transformers, again at 28 seconds, and I might say, should some of these transformers be shed? The idea isn't that you're going to shed them at 28 seconds. The idea is you're doing this sort of analysis to come up with some general mitigation plans that could be implemented. Here's again at 28 seconds, I didn't pause, I restored the power flow, and I'm looking at it and I'm visualizing with the yellow arrows how the GICs are flowing through the system. The rectangles are geographic data views where the size of the rectangle is proportional to how much reactive power is being lost at that bus due to the GICs. And then the color is the voltage level. This is kind of the Dallas area, so it's kind of ground zero. So there's a lot of GIC losses there and a lot of depressed voltages. Summary. You know, the tools are out there to do this sort of analysis, and they've come a long ways in the last year or two. So if you're interested in doing HEMP analysis, the tools are available. And that's our control lab that we have here at Texas A&M. We took that during NAPS when we were doing some demonstrations for some of the NAPS attendees, and we expect to do the same at TPEC. So hopefully there's time for a few questions. Scott, are you still there?
I'm still here, yeah, and I'm watching the chat too. So if you'd like to ask a question, feel free to either unmute yourself and ask, or place it in the chat, and I can just repeat it for
Mic check. Mic check 1 2.
Yeah, I'm coming through.
Okay, great. So my name is Manuel Franco from the Defense Star Reduction Agency, and I have a question in regards to slide number 9. Obviously, you talked about how we get to the event, but one of the things that is of interest to us is how long would it take post-event to rebuild transformers and transmission lines in the event that the grid is damaged?
Yeah, and that's a great question. And I don't have to go to slide 9 because you're just asking the restoration issue. what we would do is we would simulate an event, and it depends on the size of the HEMP. In some of the public waveforms, like from the Ditcher document, there's not going to be any rebuilding because nothing got damaged. In terms of the damage to the transformers, what we can do is we can do a heating analysis on the transformers. I didn't talk about that here, but we've done that for GMD. The transformer heating depends upon the GICs that are going through the transformer. And if the transformer is damaged, then, of course, you're going to have to replace it. And that would be a more involved process. Most people will say not a lot of transformers are going to be thermally damaged because of the problem duration, but that certainly depends on the event. The transmission lines themselves should be okay from the E3. Whether relays and stuff are affected by the E1 depends upon the particular relays and how they're shielded.
Hey, Mike, check. Tom, this is Chris Owens. I got a question for you, if you can hear me.
I can.
Yeah, so I was kind of interested. I thought it was kind of very intriguing relationship you talked about between the E1, E2, and E3. And I liked the example you showed about the E1 and the potential initial condition damage. And I was just curious on your thoughts on the geospatial relationship between E3 and E1. I mean, it looked like you just sort of picked a random spot, but if we, if you looked at,
I did pick a random spot. This, as I said, wasn't meant to replicate any particular scenario. So yeah, I definitely picked a random spot. But yeah, I mean the point, if we were doing a real study for somebody who could say, this is the E1 and it's in this spot, and this is the E3, and they express the E3 as a B3D file, then we'd go from there.
Okay, thank you.
Tom, there's a question in the chat about, is there anything to simulate protection tools such as neutral blocking devices? I can answer that by simply just saying yes. As far as neutral blocking devices go, protection tools, I guess it could be broader than that, like relays and things like that. Generally, a lot of that relay protection can be put into the transient stability analysis, but a lot of it is not. I guess a lot of it that might operate over longer periods of time that might be important in an HEMP event. It's been our experience, so like zone 3 relays and things like that, generator over frequency, under frequency devices, generally not populated to great detail in transient stability models yet. But if you do have that information, in theory, it could be put in there, and I think it would probably benefit the industry as the focus on HEMP events grows and the focus on preparedness grows. Then certainly populating the transient stability models with those details would be important. But neutral blocking devices are pretty straightforward. Those operate kind of in the DC time scale. And yeah, in PowerWorld Simulator, you just click on a transformer and you say that it has a neutral blocking device, and
yeah, and that would be an input. And I didn't mention neutral blocking devices, not because I'm against neutral blocking devices. There's just not a lot of them out there. But in a study point of view, if somebody said, hey, I want to study this GIC scenario or this HEMP scenario, and I want to put a neutral blocking device here, here, or here, we could either set them up as they would, as Scott said, be set up as an initial condition, and then you just do a study with it either in service or out of service. Another important point, which I mentioned right at the beginning, is when you do these studies, it is really important to make sure that your generator step-up transformers are in the correct configuration. And for most generators, if they're out of service, their GSU is out of service as well. So in the power flow, they need to be modeled correctly, because that transformer becomes another path to ground. Now with the HEMP, sometimes you want, you know, paths to ground because you want to shunt some of these GICs to ground. I did have on the slides a brief mention that not all transformers are created equal. There are some transformers that are much better able to handle GICs from a heating point of view and also from a reactive power consumption point of view. Those might be the transformers that you want in service so that they shunt the GICs into the ground, because ultimately the GICs are, you know, being induced in the high voltage transmission system, and they're going to ground one way or another. And the idea is that we want to control how they go to ground. Yeah, we didn't lose you, did we?
No, I'm still here. I don't see any other questions. Does anybody else have any other questions for Tom, or general PowerWorld Simulator questions?
Well, hearing none, I appreciate everybody listening on a day when it's certainly maybe not a high impact, low frequency event day, but we're getting some significant weather across the country. So I appreciate y'all listening. The slides and I guess the recording will be available on PowerWorld's website, and I will upload the case that I used so that people can have access to it if they want to play around with it.